Imagine the Eiffel Tower. Now, imagine a passenger train driving across the very top of it. Connecting the isolated Kashmir Valley to the country railway network was a decades-long ambition, but for years it remained only a dream. The primary obstacle was this: the deep, brutal gorge carved out by the powerful Chenab River. This specific slice of Himalayan geography renders conventional engineering useless. To cross this abyss, engineers had to throw out the old rules and outmaneuver the landscape. The drop from the required track level down to the riverbed is a staggering 359 meters, well over 1,170 feet. Standard bridge design uses concrete pillars in the riverbed, but the violent force of the Chenab's rushing water would scour away conventional foundations before setting. Even if a foundation could be secured, a concrete pillar reaching this height would succumb to its own dead weight, crushing its own base before a train ever rolled across it. With the riverbed and gravity working against them, engineers abandoned bottom-up construction entirely. The only path forward was to rely exclusively on the solid rock of the surrounding cliffs. The solution was a massive steel arch, designed to hover high above the gorge without a single support touching the water. This diagram shows the physics at work. When a train crosses, the arch design takes that immense downward weight and redirects it outward, transferring the energy into the solid Himalayan rock on either side. But at this altitude, the gorge acts like a wind tunnel. Air currents rip through the valley at up to 260 kilometers per hour, Category 5 hurricane speeds that would catch a solid structure like a giant sail. To survive the wind, the bridge utilizes a truss structure. Instead of solid walls, it's a precise web of steel beams. These empty spaces allow high-velocity winds to pass safely through the frame, preventing the air from catching the bridge. The physics held up on paper, but translating that design into reality meant figuring out how to assemble thousands of tons of steel in mid-air. The materials had to be rated for extreme temperature swings, from minus 10 degrees Celsius in the winter to 40 degrees in the summer. For security, engineers used specialized blast-proof steel certified by the DRDO, ensuring the structure could withstand explosions as well as the climate. Moving these massive steel components was the next challenge. There were no direct roads to the site and no way to build scaffolding from the ground up. The answer was the world's largest cable crane system. Giant pylons were erected on either side of the valley to string thick steel cables across the gap. This massive zipline allowed workers to hover 300 meters above the gorge, carefully dropping massive steel segments into precise mid-air positions. Yet, getting the steel into the sky was only one step. The trim test was fighting gravity to keep it there during the entire assembly process. Using a cantilever method, both halves of the arch were built outward into thin air, moving from the edges of the gorge toward the center. As more steel was added, the weight grew. Without support, gravity would pull the advancing structure downward until it collapsed. Engineers countered the pull with thick tie-back cables anchored deep into the mountain rock, physically pulling the advancing bridge backward. It was a high-stakes tug-of-war. The steel's weight pulled forward, while mountain anchors held the project in place. This delicate balance had to be maintained for years, right up until the moment the two halves finally reached each other. At the center of the gorge, the two massive halves of the steel arch hovered inches away from one another. The margin for error was almost non-existent. If calculations were off by mere millimeters, or if thermal expansion shifted the metal, the bolt holes would fail to align. But the two sides met perfectly. The final piece, called the golden joint, was fitted into place, locking the arch into a single continuous structure. Then came the final step. Engineers slowly released the tension on the tie-back cables that had been holding the bridge to the mountainside. As the cables loosened, the two halves pressed into one another. The load shifted, and the arch finally supported its own massive weight. That single joint represented the victory of mathematics and grit over the unpredictable chaos of the natural world. The completed bridge now stands as a permanent part of the Himalayan landscape. Trains are now crossing this abyss, ending the decades-long isolation of the Kashmir Valley. If we can build a railway 359 meters high in the middle of a Himalayan storm, where exactly do our infrastructure limits lie? The Chenab Bridge is the result of a specific set of geographical challenges, meeting a specific set of human solutions.
If you enjoyed this deep dive into the impossible and want to discover more incredible engineering marvels, mega projects, and construction achievements from around the world, make sure to subscribe to Built by Engineering. We'll be bringing you many more visually stunning stories of human ingenuity and engineering excellence. Until next time, keep marveling at what we can build.